All right. Today's section talks about measures of position. You may have heard these in the past where they talk about quartiles or fractiles. A lot of times this is used in SAT scores. So most recently you may have seen it there. So fractiles are numbers that partition or divide an ordered set of data into equal parts. Quartiles, therefore, approximately divide our data into 4 equal parts. The first quartile, the second quartile, and then the third quartile. So just like you would think, it's about half. It's 1/4 in the first quartile, half the data in the second quartile, and then 3/4 of the data in the third quartile. So our first example talks about automobile commuters, and the amount of gas that they waste due to traffic congestion. The amount in gallons each year of fuel wasted in the 15 largest urban cities is listed below. Find the first, second, and third quartile of the data. And then what do you observe? So in order to answer this, we do want to put the data in order. So we're going to start first by putting the data in order if it is not in order. So we have 11, and then we have 20, and then 22, and then 23, and then 24, 25 appears 3 times. We have 28, 29, 30. No, wait, I'm sorry, 29 appears twice. 28, 29 appears twice, then 30. 35 appears twice as well.
So once our data is ordered, then just like we found the midpoint, we're going to, or the median, we're going to count and get to the middle of the data. So the middle of the data then, there's 15 pieces of data. So the 8th piece of data would be in the middle, 7 on each side. So 1, 2, 3, 4, 5, 6, 7 on this side. And then coming from this direction, 1, 2, 3, 4, 5, 6, 7 on this side. So the 25 right here is the median. And so your second quartile does end up being your median. From there, then, your Q1, or your first quartile, is going to be midway in the next set of data. So again, there are 7 pieces of data here. So halfway would be the 4th piece of data. 3 on this side, 3 on this side. So this is the 4th piece of data, making 23 the first quartile. Similarly, if we look at the last quartile, or the third quartile, again, there's 7 pieces of data, so that would be 3 on the left side, 3 on the right side, leaving Q3 here in the center at 30. So if we wanted to know what data fell within the third quartile, then that would allow us to know that 30 is in the third quartile, and so everything below 30 then would fall into the third quartile. So how do we use technology to do this? We already showed how to do your calculator with entering your data. And you may have already recognized that we're going to do the same thing, because when we enter the data,
we end up with going back to that one variable statistics, and you may have seen Q1 and Q3 on there. So if we do stat, again, edit, I'm going to clear this list. So remember to go up to the top of, so tab up to the top of the list, hit clear, and then hit enter, and my data clears out. So now I will enter all of the data. This is the tuition costs for the 25 liberal colleges. So 50. It's going to take just a second to enter this. 51, 49. 52, 51, 25, 41, 36. All right, so I now have all 25 pieces of data entered into the calculator. Again, list 1 on 26 tells me that 26th piece of data is blank. So there are indeed the 25 pieces of data. If I now go back to the stat edit button, one variable statistics. Again, as long as I'm in list 1, I don't have to change anything. And now if you look down here at the very bottom, it does tell me that Q1 is 28.5, and the arrow means there's more information. And so Q2 is the median, so that's 36. Q3 is 48. It also tells me my min and my max, which we're going to use here in just a minute. So Q1 was 28.5. Q2 was 36. Remember again, this we got from the median. Spell it quickly. And Q3 was 48. All right. Interquartile range, then. That's a measure of variation that gives the range of the middle portion, about half of the data. So basically half. This gives us the middle half of the data. We find this by taking Q3 and subtracting Q1. We also can use interquartile range, then, to identify outliers. And any data that is less than the first quartile minus 1.5 times the interquartile range is an outlier. Any data greater than Q3 plus 1.5 times the interquartile range is also an outlier. So let's take a look at the interquartile range from the first example. So we're going back to the gasoline fuel waste. And we said that Q1 was 23, Q2 was 25, and Q3
was 30. So the interquartile range is going to be Q3 minus Q1, which is 7. So there are 7 pieces of data that fall in that area. So now we can find out what the outliers are. And so if I take Q1 and I subtract 7
times 1.5, or if we let it look like the formula, formula says 1.5 times the interquartile range, which was 7. So that would be 23 minus 10.5, which is 12.5. That would be an outlier. Likewise, if I did Q3 plus 1.5 times 7, that would give me 30 plus 10.5, or 40.5. So now anything less than 12.5 or greater than 40.5 is an outlier. So if I look at my data, my original data, there is nothing larger than 40, but there is one number less than the 12.5. So in our set of data then, 11 would indeed be an outlier. Everything else lies pretty well in the information. All right, one of the things that we do then once we find all this data is it allows us to create what we call a box and whisker plot. A box and whisker plot. So then we need the minimum, we need the first quartile, we need the median, we need the third quartile, and we need the maximum. So that's, again, one reason that one variable statistics on your calculator gives you that information. So in our example, the minimum was equal to 11. Again, Q1 was 23, Q2 was 25, Q3 was 30, and the maximum piece of data was 35. So we're going to put this on starting out on a number line. I count by 10, 15, 20, scaling it as we go. So this is called a box and whisker plot because there will be a box in the center, and the box part is created with the quartiles. So if I go to 23, and I put a dot, I put a dot at 25, and another dot at 30. This is with which I'm going to draw my box around. So again, 23, 25, 30. And then the whisker part goes to the max and the min. So my max in this case is at 35. So there's my whisker. And then the other one goes all the way down to 11. Here would be my other whisker at 11. Next we can label it. This is gallons of fuel wasted. And that is a box and whisker plot. centered around quartiles and around the data, the middle portion of data. All right, understanding and interpreting percentiles. So again, a percentile then breaks it up rather than into quartile into 100ths. So that allows us to look at things like SAT scores because we want to compare that over the entire population of people, which would be 100% of the people who took it, 100% of the population who took it. So an OGOD, remember, represents the cumulative frequency data for SAT scores. What is the score that represents the 80th percentile? So if I look at percentile going across my graph, and then going down from there, that's at about 1250, not quite 1300, maybe 1260. So it says approximately 80% of the students have an SAT score that's 1260 or less. So the higher the percentile, obviously the better your score is when compared to people who took that test that year. So everything is dependent upon the entire population of students who took that test that year. So if someone took it a different year and scored the exact same that you did, they may be in a different percentile. Percentiles that correspond to specific data entry. To find a percentile that corresponds to a specific data entry, we're going to use this formula. So this is going backwards. So this time I want to know if I scored a 1200 on my SAT, what percentile does that put me in? So to find that percentile, you're going to take the number of data entries that are less than your value and divide it by the total number of entries. Then because it's a percent, we're going to multiply by the 100. So in this, for the data set in the second example, find the percentile that corresponds to 34,000. So this one we're going back to the tuition data. And so if I look at the tuition data, then I will find out how many pieces of data are less than 34,000, and I'm going to divide it by the total number of data. So let's go back up. Less than 34,000. So we have 1, 2, 3, 4, 5, 6, 7. Make sure I didn't miss any of them. 3. So there would be 8 pieces of data. So there are 8 pieces of data that are less than 8 entries or pieces of data less than 34,000. So we're going to take 8. The total number was 25. They told us that. We're going to multiply that by 100, and when we do, we get 32, which of course would be 32,000. Since we're talking money. Oh, no, we're not talking money. That's a percentile, not money. Sorry. Got you all confused now. This is the 32nd percentile. So the conclusion then says that tuition of, here's my $34,000 tuition, is in the 32nd percentile, kind of abbreviating there. So therefore, tuition of $34,000 or more is greater than 32% of all tuition costs. So if you have a place that's got $50,000, then that's going to be obviously more than the $34,000, so it's greater than 32% of all tuition costs. So if you want to know which ones are the cheapest, then 1/3 of them approximately would be less than $34,000. All right, and that's going to take us to a standard score, sometimes known as a Z-score. And this is going to represent a number of standard deviations given value X falls from the mean mu. To find the Z-score, we're going to use this formula. We're going to take the value, our entry, our X entry, we're going to subtract the mean, and then we're going to divide by standard deviation. This is going to help us interpret charts as we go through this. So Z-scores can be positive, negative, or zero. When a Z-score is negative, the corresponding value is when the Z-score is negative, the corresponding value is less than the mean. When Z is positive, the corresponding value is more than the mean. And for Z equal to 0 is exactly the mean. So it's equal to the mean. A Z-score can be used to identify an unusual value of a set of data that is approximately bell-shaped. So again, we're going back to that approximately bell-shaped. So the empirical rule says that about 95% of the data is going to fall within 2 standard deviations from the mean. And so it allows us then to look at a value maybe that falls right here. If I can't count exactly the 1 standard deviation either direction, then where are these values? What do they look like? The same thing here. What does this value look like? So being able to convert things from X scores from your data to a Z score is going to allow us to do that. About 95% of the Z scores then are going to fall between -2 and +2. So now we're finding them, we're going to actually see the position that they are according to the standard deviation rather than the actual X value. So the table below shows the mean heights and standard deviation for a population of men and women. Compare the Z-scores for a 6-foot-tall man and a 6-foot-tall woman. Assume the distributions of the heights are approximately bell-shaped. So if we look at the men's height, well, it says that the average man is 69.9 inches tall with a standard deviation of 3 inches. So I want to know then where a 6-foot-tall man falls. How many standard deviations is the 6-foot-tall person from the mean? Well, in order to do that, because we're in inches, we do need to convert 6 feet to inches. So 6 feet is equal to 72 inches. 6 times 12. So looking at a man, I'm going to take the 72. I'm going to subtract 69.9, divide it by 3.0. And that's going to tell me that I have 0.7. So we interpret this then to say 6 feet tall men are within 1 standard deviation of the mean, which then would be a usual height. It's what you would expect it to be. So if we look back at our little chart here, 0.7 would be right about here. And again, that's a usual score. So what do you think is going to happen with 6 feet tall women? Well, it's going to be very different because now a 6 foot tall woman is going to be very different from the mean. So let's look at the women. This time we're going to use women's height. So the mean again is 64.3. So we have 72 minus 64.3. Their standard deviation is only 2.6. So when I do that division, it's approximately equal to 3.0. So this conclusion says that 6 feet tall women are 3 standard deviations from the mean, and therefore that is an unusual height. And so again, if I look at my little table here, 3 standard deviations would be right here. So it's on the border of unusual and very unusual scores. And so in reality, again, this is going to tell us that how many 6 feet tall women do you see, basically. If we look back on our chart, and we put this in the percents, remember that 95% will fall within 2 standard deviations. That's our 95%. And so there's not going to be very many women between here and here. That goes to the 99.8. So there's going to be very, very few women, less than 2%, that will fall within that standard deviation. Roughly 2.5 if you don't go to quite the 0.8. So less than 2.5% of women are expected to be six feet tall. And again, that should make sense to us. So it's taking an actual physical number, the actual height, and it's comparing it to standard deviations so that we can then compare it to where does it fall within that data set. 6 foot tall man is really unusual. 6 foot tall woman is really unusual. And that wraps up chapter 2.